In Lab 3, we will primarily study Kirchhoff's voltage law and Kirchhoff's current law, but in doing so we will gain experience in breadboarding and using test and measurement equipment in the lab. The pre-lab was a bit complex and the schematic may have been a challenge to complete. That is, unless you looked ahead to the Lab 3 procedures, where the circuit schematic was already given. Well, almost. I'm also going to suggest a slight change in the resistor values that will slow your car a bit more and hopefully give you better results in the lab. And instead of following the physical layout suggested in the pre-lab, I'll walk you through what I hope is a cleaner design layout. With your power rails on the right, insert a button near the top of your breadboard. Place the other button near the bottom. Insert a 220 ohm resistor so that one lead connects to a pin of the button. Let's see that up close. Add 3 more 220 ohm resistors, then repeat for the top button. We'll need more connections for the non-button end of these resistors, so choose a wire color and create a jumper across the center of the board. While the wire color doesn't really affect function, don't use black or red because they generally represent nodes at the negative and positive ends of the battery. In my design, I used orange jumper wires. Connect the positive rail using a red wire to the button end of the 220 ohm resistors. Between the other node of the button and the orange node, connect 2 100 ohm resistors. These resistors will be in parallel with the 220 ohm resistors only when the button is pressed, causing both wires of the button to be shorted into a single node. Since we don't have motors at home to test our circuit, use your blue LEDs as a substitute, placing the long lead in the orange node and the short lead in the negative battery rail. Power your circuit and observe how current through the 220 ohm resistor network allows the LED to be illuminated. Pressing the button adds the 100 ohm resistors in parallel with the 220 ohm resistors, thus decreasing the network's overall resistance and resulting in a brighter LED. In the lab, you will replace your LEDs with motors and verify that the buttons also increase current and therefore wheel speed when pressed. There is no need to remove the button when adding snap action switches. Merely place the common wire at one button pin and the normally open wire at the other button pin. This will allow the switches to override your buttons. Enjoy testing your car on the obstacle course, but return to your bench to learn more about the oscilloscope. The oscilloscope displays voltage versus time, which makes it much more valuable than a voltmeter when your voltage changes across time. To use the oscilloscope, turn it on using the button on the lower left, but then press the default setup button near the upper right. This will clear any confusing settings used by the previous owner. There are 2 main knobs to learn about today. The first sets the scale on the y-axis, or the voltage axis. The other sets the scale on the x-axis, which is the time axis. Play with these knobs and watch the screen to see how the volts per division and the time per division changes. As you press the snap action switches, you will see corresponding changes in the voltage across the motor. Continue to adjust the vertical and horizontal scales until you get a clean view of the changing voltage signal. Now remove the switches, buttons, and the smaller resistors from your circuit. Change the power connections if necessary so that they still reach your resistor network and cause your motors to run. It is this circuit for which we will apply Kirchhoff's laws. When using the voltmeter, remember that the negative voltage symbol is where you place the black probe and the positive voltage symbol represents the red probe. Moving the 2 probes around your circuit, measure the voltage across your battery, across the motor, and across the resistor network. To apply Kirchhoff's current law, we will use the ammeter to measure the current flowing into the battery. The ammeter uses a different connection point on the meter. For the ammeter, the end of the current arrow represents the location of the black probe, and the start of the arrow the red probe. You must break the circuit to insert the ammeter. To do so, move the positive connection of the battery to an unused node on your breadboard. Following the schematic, connect this to the black probe of the ammeter. The red probe then returns to the power rail, allowing the current measurement while still applying battery voltage to the rest of the circuit. The voltages you measured earlier can be used to estimate the current through the resistor networks through Ohm's law, so there's no need to use the ammeter again. With so many students using the ammeter, a blown fuse becomes a distinct possibility. To test for a good fuse, set up your multimeter with probes on the voltage in common locations, then check for continuity. If you hear the tone, your fuse is good.